Good morning, ladies and gentlemen. It is my great honor to receive the invitation to give this plenary speech. I'm delighted to share with you an emerging topic called electric spring and smart load, which is a topic that my research teams at Imperial College and Hong Kong University have been working on for the last few years. In this presentation, I will first give you the background of the research and the grand challenge. Then I will introduce the basic concept of electric springs. After that, I will show you some practical measurements based on hardware test. And after we have done the modeling based on the practical measurement, our research team and some other research institutes and universities have also used the model to study electric spring technologies in power systems. Okay, so I will show you some results based on the simulation. And then I will conclude my presentation with several remarks. I'm sure we're all aware of the urgency of climate changes. We know the rapid disappearance of ice cap in the North Pole, South Pole, and Greenland. There's also one more issue about the climate change, which is the high concentration of CO2 in the atmosphere. It has exceeded 400 ppm, which is the dangerous level several years ago. And now this CO2 is now being absorbed in the seawater. So the acidity of seawater is increasing. And according to the EPA, the high concentration of CO2 in the seawater will reduce calcium carbonate. And calcium carbonate is a building block for the shells and skeletons of many marine organisms. That means the bottom of our food chain is now being threatened by climate change. One effective way to reduce greenhouse gas emission is to increase the use of wind and solar power rapidly. And one good example is Germany. They have set very ambitious target to increase wind and solar power. But we can also see the problem now when start to increase the amount of wind and solar power. Several years ago, there was a report about the green energies destabilizing the electric grids. And it is because of the intermittent nature of wind and solar power. Okay, so the intermittent power is causing destabilization of the electric grid. Intermittent power means the changing nature of wind and solar power. Okay, so they are potential threats to the power stability that may end up in blackouts and damage of industrial equipment. As a matter of fact, in year 2013, the power system in Hawaii collapsed when the wind power reached about only 17%. And in another report, it also indicates that the instability issue from the German grid is now exporting to the neighboring country. Okay, so Poland and the Czech Republic are spending more money to protect their power system from the German power surges. Okay, so we can see intermittent nature of wind and solar power could cause instability to the power system. Because one fundamental requirement of power system stability is to balance power supply and demand in real time. Okay, so the question we need to ask is how much percentage of wind and solar power we can achieve without causing instability. So if we look at a basic concept through this simple video, if we consider the water level as the voltage or the frequency, to keep the water level stable, we need the supply and demand to be equal. Otherwise, the water level will fluctuate. Similarly, for electrical system, the electrical generation and the electrical demand must be balanced in real time. Otherwise, the voltage and the frequency of the power system will fluctuate as well and become unstable. Now, when I was asked about the question over 10 years ago by a very famous professor, Professor Felix Wu of UC Berkeley, he says that if we cannot handle the intermittent nature of wind and solar power, we will have big trouble because when we inject more wind and solar power to the system, we are increasing the danger to the stability of the power system. And that gave me many sleepless nights. Then suddenly I realized that one obvious solution is to look at the mechanical springs under our bed, because the mechanical springs under our bed form a highly stable structure. So I went back to the Hooke's law. If you look at the Hooke's law, which was published in 1660, Hooke's law was about the physical behavior of a mechanical spring. And we all know that mechanical spring can be used to provide support and to absorb vibration. Okay, so we have been using mechanical springs every day. Okay, so this inspired me to consider developing an electrical version of the mechanical spring to provide support and to absorb vibration in power system. One interesting thing about the spring is that they can work individually, but with many of them distributed, they can also provide a highly stable structure collectively. That means individually they are okay, collectively they are also stable. Okay, if some of them fail, the overall structure is still stable. Okay, so this is a interesting feature of a group of distributed mechanical springs. So I want to turn this concept into an electrical version to stabilize the power grid. So if you consider the emerging grid with more wind and solar power, so now we can see that the total power generation will no longer be stable because we cannot predict wind and solar power accurately. In the past, without using renewable, the power company can control the power generation very accurately. Okay? Now we have all these fluctuating factors, and that could cause instability in the voltage and the frequency of the power supply. Now, power company and power industry are aware of this issue. Okay? So they have developed demand side management to deal with the needs for balancing power supply and demand and for peak power shaving. They have developed some existing solutions. Examples are load scheduling, which are for days and hours ahead. So that means load scheduling cannot be used as an instantaneous power balancing solution. They can use energy storage to reduce the peak power, but energy storage is not cheap. It is a fairly expensive option. They can use real-time pricing, but it is not guaranteed because in a hot summer day, people will still turn on the air conditioning. The power company can turn off electrical appliances, but it is an intrusive and inconvenient solution. Now, when some countries are talking about using 100% renewable energy, and we need to ask the question, what technology do we need to achieve this power balance and to reduce voltage and frequency fluctuation? So we need to change the control paradigm. If we compare the existing power generation and future power generation, we can see the difference. In our existing power generation, it is basically a centralized system. That means power is centrally generated in the power station, and then the power flow is one way from the power station to the load cell. And the control paradigm has been power generation following load demand. Now, with the emerging grid, power grid with more distributed renewable energy sources, we have a more distributed power generation in the system, and the power flow will be bidirectional. Okay, that means the power can flow back from the center into the grid. And then the future control paradigm must be changed. It has to be load demand following the power generation. Okay, load demand following power generation. So we need to develop new technology to make the load demand adaptive so that the load demand can follow the power generation in order to achieve instantaneous power balance between supply and demand. Okay, so this is where the electric spring technology was motivated. Now, in the next section, I will explain the basic concept of electric springs. We want the electric spring to have the same features or functions of mechanical spring, that is to provide support and to absorb vibration. We want these springs, electric springs, to be small, and they can be distributed over the power grid. And we want them, many small but distributed electric springs, to provide collectively a highly robust and stable structure for the power grid. Now let us compare the basic equations. For mechanical spring, when it is in a neutral position, the displacement is 0. If we compress it, a force will be developed to restore the spring to reduce the displacement. If we extend the spring, the force will develop in the spring will pull the spring back to the neutral position. Okay? So the equation is, the force equation is equal to negative kx, where k is a constant, x is the displacement. And the potential energy stored in the spring is half kx squared. Now, ideally, a spring will not dissipate energy. Ideally, okay? It can store energy, but it doesn't dissipate energy. Now, in the electrical version, we can consider the voltage across a capacitor as electric spring. If the mains voltage is correct and stable, the spring voltage becomes 0. If the mains voltage is lower than the nominal value of the mains voltage, then we can develop a voltage here so that the load voltage vector and the voltage vector of the spring will be equal to the nominal value of the AC mains voltage. And similarly, if the mains voltage exceeds the nominal value, the spring voltage can be negative to pull it back. Okay, So compare the two sets of equations. In the electrical version, we can have the charge equal minus CVA, where C is a capacitor, and V is the voltage across the spring or this capacitor, and the energy storage is half CV squared. Now, the spring can be provide both active and reactive power compensation depending on the structure of the electric spring circuits. Okay, so we want the spring to provide both active and reactive power compensation. There are various versions of electric spring over the last 8 years. The first version is very simple. We just have a simple inverter, which can be a full bridge or half bridge inverter with a LC filter. And here the DC link can be provided by a simple DC capacitor. In this case, we don't need active battery storage, like we don't need a battery basically. So the inverter can do PWM pulse width modulation, and through the filter, the low pass filter, we can generate a 50 Hertz or 60 Hertz voltage across the capacitor, and that becomes the voltage across this electric spring. Now the electric spring is associated with a load that we call non-critical load. Okay, so for the first version, you can see basically we don't have any lossy component except the switching loss, of course. Okay, and the parasitic resistance here. But ideally, it is a lossless circuit, just like an ideal mechanical spring. Another version is to replace the DC capacitor with a battery. Now, in this case, we can provide both active and reactive power compensation, and we have a wider operating range. The price we paid is a battery storage. If you don't want a battery, we can also use a back-to-back configuration. Okay, so we can use two inverter. One is in a shunt arrangement, is a series arrangement. In that case, we can provide full active and reactive power support, and we have fast dynamics, no energy storage such as battery. Now, this circuit may look complicated, but in practical implementation, it can be done with only 6 switches. Okay, so it is still a low-cost solution. Now, one major difference between electric spring and existing FACS devices is in the control loop. In FACS device, if we have a fluctuating input, the normal control strategy is to regulate the output. Okay, so control loop is put in the output. This is the existing FACS device technology. It is different in the electric spring technology. Here, if we have a fluctuating mains AC voltage caused by the intermittent nature of wind and solar power, we want to regulate the input voltage to stabilize the local input voltage and let the output of the spring to fluctuate. Okay, so we stabilize or we regulate the input voltage and let the output fluctuate. Okay, so the idea is to allow a well-regulated output, we call the standard mains, to provide power for the critical load, and we provide a fluctuating mains, which we call the adaptive mains, to power the non-critical load. So the basic concept is to let the non-critical load to absorb the power fluctuation caused by the wind and solar power generation. Okay, so it's a very simple concept. So if we turn it into a simple form, we have the standard AC mains and the adaptive mains. The standard AC mains will provide stable power for the critical load, and the fluctuating or the adaptive mains will provide power for the non-critical load to absorb all the power fluctuation. Okay, so it's a very simple concept. Now, what are the non-critical load? If you look at the distribution of a typical city, about 40 to 50% of the thermal load, like conditioning, water heater, can be considered as non-critical load. Typically, we call any electrical appliances that can tolerate a higher voltage fluctuation as non-critical load. Okay, So the idea is to let this non-critical load, particularly thermal load, to absorb the power fluctuation, because the water temperature or the air temperature will not change rapidly. Water and air have high thermal capacity. Okay, so this is the idea that we use them as non-critical load. So we allow a regulated standard means to power the critical load, and a fluctuating adaptive means to power the non-critical load. And then we can balance supply and demand in real time. Now, where should we put the electric spring? We can either embed it inside the electrical appliances, or we can put it behind the power socket. Now, after many discussion with the power companies, actually this is the structure they prefer. They prefer the electric spring to be built behind the socket as part of the power supply infrastructure. The reason is very simple. Anyone who uses the adaptive means are helping the power company to absorb more power fluctuation in the generation part. That means anyone who uses adaptive power supply will enable the power company to use more wind and solar power. Okay, so that's why they can give you a discount in electricity price if you use the adaptive means. So if we can achieve this by distributing the spring in the low voltage distribution network, hopefully we can stabilize the power system, even we increase the percentage of wind and solar power. Now let me show you some practical measurements obtained from a 100 kVA hardware microgrid emulator. What we want to do is to try various forms of electric spring to provide active and reactive power compensation in order to keep the AC mains voltage at the nominal value. That means the vectorial sum of the electric spring voltage and the voltage across the non-critical load will be equal to the nominal voltage of the AC mains. So sometimes we may have to do voltage suppression or voltage support to maintain this nominal value. Without using any communication between the electric springs, we use the group control for each unit so that each electric spring will maintain the local voltage without any communication. We conducted our test in Hong Kong University and at Imperial College. This is the set at Imperial College. This is the 100 kVA hardware emulator. So we have the configurable system to set up our microgrid. And these are some of the hardware setup. Here is a schematic of the setup. Here we have a traditional power generation, the transmission line, and somewhere in the transmission line, we inject intermittent renewable energy. Okay? And then in the load side, we have the electric spring with a non-critical load, and we have the non-critical load connected to the AC mains. So if you like, this is the standard mains, and this is the adaptive mains, which may fluctuate a bit. Okay, so we also have a bypass switch across the electric spring. So if we do not activate the spring, the bypass switch is closed to bypass the electric spring. Now here we show two sets of results before using the spring and after using the spring. So we use a pre-recorded winding profile and inject the intermittent power into the grid. So you can see for both standard AC mains voltage and the adaptive AC mains voltage, before activating the spring, they are identical. So you can see the fluctuation. And so the power consumption of both the critical load and the non-critical load are fluctuating as well. Then we activate the spring here, and you can see the bouncing action of the electric spring voltage. So this bouncing action helps the system to maintain a regulated standard AC mains voltage. And for the adaptive mains voltage, it is fluctuating. And this fluctuating adaptive mains allow the non-critical load power consumption to vary. But because we managed to regulate the AC mains voltage, okay, so for the critical load, the power consumption remains stable. In this way, we balance power supply and power demand in real time. We can also look at both the voltage and the frequency fluctuation at the same time, because in the emulator, we can include the frequency control loop. Again, we have two sets of results. For the first set of results, we did not activate the electric spring. And because of the injection of the intermittent wind power, both the voltage and the frequency of the microgrid fluctuate. And then we activate the spring at this point. you can see now that the standard AC mains voltage is now regulated closer to 220 volt. And the frequency of the microgrid is restored to 50 Hertz. The reason is very simple. Here, after activating the spring, we allow the adaptive AC mains to vary its voltage so that the non-critical load power will follow the fluctuating power profile of the renewable energy. Okay, so that's why we can balance power supply and demand in real time in order to regulate both the frequency and the voltage of the microgrid. Now, some people may say, well, we can use energy storage to absorb the energy difference between supply and demand. Yes, we also have a setup including a battery storage and a bidirectional AC to DC converter. Here in the non-critical load, we keep the electric spring with the non-critical load, and then we have a critical load. These are two sets of results. The first set is without using the electric spring. The blue line represents the input power from the generation. It is fluctuating. When the power is low, in order to maintain low power, the battery has to be discharged so that the low power can remain constant. Here you can see this is the time when the battery is discharged because the incoming energy is not sufficient. But when when the incoming energy generation is large, the extra amount of energy has to be absorbed by the battery. So this is the time when we have the charging energy getting into the battery. Now, if we enlarge this charging profile of the battery here, this is the power. And then we do the integration to obtain the energy profile. We can see that the energy capacity required in this process is very large. Now, if you look at the situation when we are allowed to use the electric spring, when the input power is low, we allow the non-critical load to reduce power consumption. In this way, the amount of power required from the battery becomes smaller. And similarly, when the input power is large, we allow the non-critical load to absorb more power so that the amount of energy required to be stored in the battery becomes smaller. Okay, so if we do the integration again to obtain the energy profile, you can see in this example, in the energy storage capacity of the battery can be reduced by half. Okay, so it means that we may still need to use the energy storage in our system, but with the use of electric spring, the storage capacity can be significantly reduced. Now, besides keeping the voltage and the frequency stable, we can still use the electric spring for other functions, such as power quality control and reducing power imbalance. The reason is very simple, because we may not have frequency or voltage instability all the time. So during other time, the electric spring circuit can provide other functions. Here we show you one example for reducing power imbalance. Here we have a three-phase system. The first set for the first three-phase load, you can see the three-phase currents are not the same. And as a result, we have a large neutral current circulating in the building. Okay. Now we activate the spring, the phase spring, to reduce the energy imbalance, the power imbalance, and can see that the neutral current is now reduced to a fairly low value. We repeat the experiment with another set of three-phase load with more current. Here you can see we have a larger three-phase current, and they are not the same. And here we have a larger neutral current due to the imbalance of the three-phase system. Again, we activate the spring here, and we reduce the current differences. And as a result, we also reduce the neutral current. Now, we are also interested in seeing how the droop control works, because individual electric springs do not have any communication, which is the beauty of the system, because we don't need central control. So here we have three set of experimental results. The first one is without activating the electric spring. So we have the fluctuating voltage for both of the in the three voltages. Here, the first set of results is we activate the spring without using droop control. The other set of results is we activate the spring with the droop control. Now, just look at the voltage regulation. They look similar. But when we look at the individual reactive power compensation, you can see before we activate the spring, they have no reactive power compensation. Now, once we have activated the spring without droop control, you can see that some of the springs work in an opposing manner. Okay, so they are fighting each other. But once we use the droop control, you can see the compensation move up and down in a coordinate manner. They don't share the same responsibility, but they are cooperating to maintain a regulated voltage. We do not rule out the possibility of using consensus control or distributed control. Okay, so in normal situation, if the cyber layer is available, we also investigated the use of the distributed control. So here we compare the droop control and the consensus control. This is the voltage. In this case, we have 5 electric springs distributed along a distribution line. Before we activate the spring, say the voltage at different points are different along the distribution line. Now, once we activate the spring, we manage to regulate all the voltage here, V1 to V5, close to the 110 volt, which is the nominal voltage in this setup. As you can see, different electric springs provide different level of compensation. Once we introduce the consensus control, again, the 5 nodal voltages are close to the nominal value of 110 volt. You can see now that they share almost equal compensation efforts under the consensus control. Now, if there's a failure in the cyber layer, the individual electric spring can still go back to the droop control. So after we have obtained all these practical results, we managed to build up computer models for the electric spring so that we can, and other researchers can also use this model to study the effect of electric spring in power system. Here we show you some examples. So we have the model with different versions of springs. Now, one question we would like to ask is, how can we compare a STATCOM with electric springs in terms of voltage regulation? So we choose a IEEE 13-node feeder system for this evaluation. The STATCOM is installed in a central manner, while the electric spring is distributed along the low voltage network. So we compare the voltage regulation. For ideal regulation, this percentage should be 0, because when this percentage is 0, it means that the actual voltage is the same as the nominal value of the AC mains voltage. Here, without any compensation along this system, the voltage regulation will deteriorate as the distance is away from the STATCOM. Okay, so now look at the effect of the STATCOM first, which is the red color here. So at the location of bus 633, which is where the STATCOM is installed, the voltage regulation is perfect, almost 0%. That means we have big compensation. As the location becomes further away from bus 633, the regulation percentage increases. Okay. Now, if we compare the use of 4 electric springs, which is the blue color, you can see the voltage regulation is fairly even, and it is around 1 to 2%, okay, which is still very small error. Now, if one of the electric springs fail, we look at the purple color. So when 3 out of 4 electric springs are activated, they can still maintain voltage regulation. Okay, so this means that if I have a STATCOM and if it fails, the red results will turn back into the green results, just like without any regulation. But for the electric spring, if all of them are working together, we have very good voltage regulation. But even if some of them fail, then we still achieve some degree of voltage regulation. And we compare the total amount of reactive power required for this level of compensation, we can see a huge difference. For the STATCOM, in this case, we require over 500 kVAR. But for the total compensation effort using 4 electric spring, it is only 88.6. Okay, so that means using distributed electric spring can be more cost effective than using a centralized STATCOM, and they can provide a better average voltage regulation over all the voltage nodes. Then we use a more realistic data provided by the China Light and Power in Hong Kong. So we use the Salo Bay power system, which is a low voltage distribution network in Hong Kong, with realistic data to compare a centralized STATCOM located in Pond A with 24 electric springs distributed in the load center. Here are the results. Without any compensation, we can see the voltage regulation. That means the error, the percentage. If we activate the STATCOM at this point, okay, you can see that STATCOM is successful in reducing the voltage error. But when we use electric spring, distributed electric spring, we can achieve even better overall voltage regulation for the entire network. Again, the amazing thing is that to achieve this type of voltage regulation, the STATCOM require almost 700 units of reactive power here. But for total of the reactive power consumed by all the electric spring, it is less than 10%. Again, it demonstrates that it is more effective to use distributed electric spring for voltage regulation than a centralized STATCOM. One major challenge of using solar power is the overvoltage issue during noontime. And also when we have electric vehicle charging, that may also cause another issue. There are two issues we consider in the next study. Here we have the high power solar panel, and also we have EV charging. So we have two issues. The first issue is the large current injection, the PV generation during noontime, because the distribution line has high resistance. So this injection of PV power could cause overvoltage problem during noontime. And in the evening, when many people charge their EV electric vehicles, we could have a voltage dip. So how to maintain the voltage within plus and minus 5% tolerance become a challenge. Here we demonstrate the effectiveness of using electric spring. With the normal load without any compensation, you can see the red color. It will go beyond the plus 5% during noontime because of the injection of the PV power. And in the evening, we could have a large voltage dip exceeding minus 5% because of the charging of the electric vehicle. Now, if we use the back-to-back electric spring, which is the black color, we manage to limit the voltage within plus 5% and minus 5%. The reason is that during the noontime, we allow the adaptive power, adaptive mains voltage to go higher so that the non-critical load, such as a water heater, can absorb more power. And during the evening, we reduce the adaptive mains voltage so that the non-critical load consume less power, so that we have more power for the electric vehicle. In this way, we keep the voltage fluctuation within plus and minus 5%. An important question we need to ask is, to achieve such voltage regulation, what will be the power rating of the electric spring circuits? And in this case, we develop a value based on the total load. And we discover that the total amount of power rating of the converter is about 60%. Okay, so that means the power rating of the converter can be much lower than the actual low power consumption. Recently, we have a new breakthrough. So far in all my discussion, I separate the load into non-critical load and critical load. Now, to some people, it is not convenient. So we did a study. If we limit the voltage regulation of the adaptive power supply to be within plus or minus 5%, effectively, it has the same function as the well-regulated standard AC mains. So we put all the load here under this adaptive power supply, but with a plus or minus 5 voltage tolerance. Here, we use it to study the entire United Kingdom power system. In this study, we assume one of the large generator of 1.8 gigawatt failed. Okay, so we don't differentiate the load into critical or non-critical load anymore, because the voltage regulation is well within plus or minus 5% in the electric spring's voltage output. Now, without the spring, we notice that if we lose one large generator, there will be a large frequency swing. So the frequency changed from 50 Hertz to about 49.5 Hertz. And we cause a sharp change in the rate of change of frequency. Now, this rate of change of frequency would be dangerous to some equipment. Okay, so we have to limit its value. But if we use the electric spring, we can actually reduce the voltage, the frequency fluctuation significantly, and at the same time, significantly reduce the rate of change of the frequency, like this. We can even quantify the amount of virtual inertia of the non-critical load. Now, in a paper which will appear next month in the IEEE transaction on smart grid, we actually provide these results. So we use the electric spring, and we limit the voltage fluctuation to be within the normal plus or minus 5% tolerance. And then for the UK national grid, we find that the total inertia or the total virtual inertia that we can derive from the use of the electric spring technology can be as high as 2.5 seconds, which is a significant value in terms of inertia. But this is the virtual inertia that the electric spring can bring to the system. We also study a small microgrid. It has an inertia coefficient of 1.3 seconds, and we found that the virtual inertia that can be added to this system based on the electric spring technology is 0.53 seconds, which is 40% of the inertia of the original microgrid. So we can see now that the use of electric spring can be applied to all load without classifying them into critical load or non-critical load. To conclude, we can see that it is urgent for us to drastically adopt more and more wind and solar power, but because of the intermittent nature of renewable energy, injecting intermittent power into the grid could destabilize the power system. Now we introduce the electric spring technology as a new way to tame the intermittent nature of wind and solar power. And we can use it to achieve the new control paradigm of having the load demand to follow power generation. And we believe that it has the potential to increase the use of renewable energy well above 20%. And we have demonstrated that electric spring can provide both voltage and frequency stability in the power system. And with this, we thank you for your attention. And I welcome any questions. Thank you very much.